Every detail in this story comes from real scientific research and observation. There is a planet in this solar system that rotates on its side. Not tilted slightly, not leaning, completely sideways, its axis tipped to 97.77 degrees, rolling through space like a sphere that never learned which direction was up. Its poles receive more direct sunlight than its equator. Its seasons last 42 years each. Right now, in this moment, deep inside its atmosphere, carbon atoms are being crushed under pressures exceeding 10 million times what exists at Earth's surface. They are not dissolving, they are not burning. They are crystallizing, hardening into diamond, and falling. Millions of diamonds raining downward through the interior of a planet you have never been told enough about. The winds in its atmosphere move at 900 kilometers per hour, and the surface of that atmosphere looks almost perfectly calm from space, pale blue-green, featureless, smooth as glass. Below the clouds there is water, but not water as you know it, water held under such pressure that its oxygen atoms lock into a rigid crystalline lattice, while its hydrogen protons move freely through the structure, a fourth phase of matter called superionic ice, simultaneously solid and electrically conducting, generating a magnetic field that points in the wrong direction and is centered nowhere near the middle of the planet. This planet has 27 known moons. Every single one of them is named after a character from Shakespeare or Alexander Pope. One of them, a small fractured world called Miranda, has a cliff face 20 kilometers tall. If you dropped a stone from its edge, it would fall for 10 minutes before hitting the ground. Only one spacecraft has ever visited this world. It flew past in January of 1986. It gathered data for approximately 6 hours. Then it kept moving, outward, away, never to return. Since that day, for nearly 4 decades, no probe, no orbiter, no signal from any space agency on Earth has gone back. The planet has been sitting there, 2.9 billion kilometers from the sun, rolling sideways, raining diamonds, holding its long, cold silence. Tonight, you are going there. This is Quiet Science at Bedtime. If this is your kind of story, a subscribe means everything right now. Just relax and feel free to let this play as you drift off to sleep. Now, let us begin. Uranus is the 7th planet from the Sun, and it has been sitting at the edge of the visible solar system for 4.5 billion years. It was identified as a planet in 1781 by an astronomer named William Herschel, using a telescope he had built himself from materials he shaped by hand in his own home. Before that night, it had been observed at least 17 times by other astronomers, cataloged as a faint star, unremarkable, assigned a number in a star chart, and left alone. Herschel was the first to notice that it moved and that its apparent disk was too large, too real, to be a distant sun. He wanted to name it Georgium Sidus, the Georgian star, after King George III of England. The international astronomical community declined. The name Uranus, the ancient Greek personification of the sky, was proposed by the German astronomer Johann Bode and eventually adopted as the standard. It is the 3rd largest planet in the solar system by radius, the 4th largest by mass. Its radius is 25,000, 362 kilometers, approximately 4 times that of Earth. Its mass is 14.5 times Earth's mass. And yet it is the least dense of all 4 giant planets, with an average density of 1.27 grams per cubic centimeter, compared to Earth's 5.5. The reason for this lower density is composition. Uranus is not built primarily from rock and metal, but from compressed volatile molecules, water, ammonia, and methane, in exotic high-pressure states that planetary scientists categorize as ices, even though they bear no resemblance at these conditions to ice as it exists on Earth. It belongs to a class of planets called ice giants, a category shared only with Neptune and distinct from the gas giants Jupiter and Saturn in both composition and internal structure. The distinction matters. Jupiter and Saturn are dominated by hydrogen and helium in metallic and gaseous forms, with relatively small rocky cores. Uranus and Neptune are dominated by these compressed molecular ices, with hydrogen and helium making up a smaller fraction of their total mass. In terms of what they are made of and how they are structured, Uranus and Neptune form a pair, the outer, stranger members of the giant planet family. You are approaching it now. Behind you, the sun has shrunk to a bright point against a field of stars. It still provides some light at this distance, roughly 360 times less light than Earth receives, but enough that the planet ahead of you is not in complete darkness. Its pale surface reflects what arrives. You can see it, not dramatically, not brightly, but clearly, floating against the black in its particular shade of blue-green, steady and unhurried. You slow your approach and simply look. The color comes from methane. In the upper layers of the Uranian atmosphere, methane gas is present in concentrations of roughly 2 to 2.5% by volume. Methane absorbs the red end of the solar spectrum, wavelengths above about 600 nanometers, and reflects the blue and green wavelengths back outward. The result is this quiet, specific color, not vivid, not dramatic, but unmistakable. It is the color of a world built partly from a molecule that on Earth forms in swamps and the digestive tracts of cattle, and here at 2.9 billion kilometers from the sun, makes a planet look like something between the sea and the sky. There is almost no visible structure in the cloud layer from this distance. Jupiter would be unmistakable, banded, swirling, the great red spot a permanent landmark. Saturn would show its ring system and its ochre belts. Uranus offers you almost nothing, a smooth sphere, a quiet face. The featurelessness is real, not a limitation of your viewing angle, but a property of the planet's atmosphere that scientists have spent decades trying to explain. And then you notice what you already know, but have not yet truly seen. The planet is not spinning correctly. Every planet in the solar system, and every moon of significant size, rotates with its axis pointed more or less upward relative to the plane of the solar system, the plane defined by Earth's orbit around the sun, called the ecliptic. Earth's axis is tilted at 23.5 degrees from perpendicular to the ecliptic, Mars at 25 degrees, Saturn at about 26.7. These are meaningful tilts. They produce seasons, they create asymmetries between hemispheres, but they are all recognizably the same kind of motion, a spinning top, leaning somewhat but fundamentally upright. Uranus is not that. Its rotational axis is tilted at 97.77 degrees from perpendicular. This means the axis lies very nearly in the plane of the orbit, not pointing up or down in any conventional sense, but pointing sideways in the direction of travel. The planet rolls through its orbit rather than spinning through it. Its poles alternately face toward and away from the Sun as it completes its 84-year journey around the solar system. For 42 Earth years, the North Pole is bathed in sunlight, while the southern hemisphere sits in continuous darkness. Then the planet rolls far enough around the Sun that the South Pole moves into light and the North falls dark, and another 42 years begin. 42 years of continuous sunlight, then 42 years of continuous night. The cause of this tilt is believed to be impact, one or more catastrophic collisions early in the solar system's history. During the first several 100 million years after the solar system formed, the space between the young planets was crowded with debris, protoplanetary bodies, planetesimals, rocky and icy objects in unstable orbits that crossed each other's paths and sometimes collided. Computer simulations suggest that Uranus was struck by a body roughly the mass of Earth, or perhaps struck multiple times by smaller objects in rapid succession with enough force and angular momentum to knock its rotational axis nearly onto its side. The collision or collisions would have been violent beyond any easy imagination. An object the size of an entire planet hitting another planet at velocities measured in tens of kilometers per second, transferring rotational momentum so thoroughly that 4.5 billion years later, the planet still rolls. Nothing has corrected it, nothing will. This is simply how Uranus is now. You watch it roll. The motion is slow from this vantage point, almost imperceptible over the minutes you spend watching. One complete rotation takes 17 hours and 14 minutes in a direction that is retrograde relative to most other planets, meaning that if you were above its North Pole looking down, the planet would rotate clockwise rather than counterclockwise. The retrograde rotation is another consequence of the massive impact that tilted the axis. The collision reversed the spin direction as it knocked the planet over. Surrounding the planet, visible now that you are closer, are the rings. Uranus has 13 known rings. They are narrow, they are dark. They look nothing like Saturn's rings. No broad, luminous sheets of ice, no obvious color, no visible gap structure that draws the eye. They are thin lines, faint and separate, orbiting the planet in its equatorial plane. Because the equatorial plane is tilted 97 degrees, the rings are tilted 97 degrees as well. They orbit vertically relative to the solar system's ecliptic. When Voyager 2 flew past in 1986, it observed the rings almost face-on, looking down into a system of concentric circles, rather than seeing them edge-on as a line. The rings were discovered in 1977, not by direct imaging, but by a method called stellar occultation. Astronomers had positioned their telescopes to watch Uranus pass in front of a distant background star, a technique used to probe the planet's atmospheric structure by studying how the star's light changed as the atmosphere passed in front of it. But before the planet's disk reached the star's light flickered. It faded briefly in a pattern of several short dips, and after the planet passed and the star reappeared on the other side, the star flickered again in a mirror image of the same dip pattern. The explanation was rings, material orbiting the planet, too dark and too narrow to see directly, but dense enough in those narrow bands to block a measurable fraction of the starlight. The astronomers had not been looking for rings. They found them because the rings revealed themselves through a star. The individual rings have designations, most numbered, some named. The Epsilon ring is the most prominent, the widest and brightest of the narrow rings, spanning between 20 and 100 kilometers in width and orbiting at about 51,000 kilometers from the planet's center. Its brightness is maintained, in part, by the gravitational herding of two small moons, Cordelia and Ophelia, that orbit just inside and just outside the Epsilon ring's edges, their gravitational influence keeping the ring material from dispersing outward. Without this shepherding mechanism, the ring would spread and fade over astronomical timescales. The ring material itself is extraordinarily dark. The average albedo, the fraction of incident light reflected, ranges from 2 to 3% in the darkest rings to about 4 to 5% in the brightest. By comparison, fresh asphalt has an albedo of around 4%. The rings of Uranus are roughly as dark as road pavement, and for the same reason, the presence of dark carbon-rich compounds that have been altered by billions of years of radiation exposure. The rings are old. Whatever formed them, perhaps a shattered moon, perhaps a captured object torn apart by tidal forces, perhaps debris left over from the formation period, has been sitting in these orbits for a very long time. You pass through the ring plane. The transition is quiet. The rings, narrow as they are, give you a moment of faint shadow as you cross each one, a brief dimming of the distant sun, then light again. Between the rings, there is almost nothing. The space inside the ring system is not filled with material the way you might imagine. It is largely empty, with the rings themselves occupying only thin bands within a much larger volume of open space. You emerge on the inner side of the rings and descend toward the upper atmosphere. The planet fills your view now. From here, the pale blue-green is not just a color, but a presence, a surface that extends to every horizon, gently curved, endless, quietly luminous in the weak sunlight of the outer solar system. You enter the outermost layers of the atmosphere. The atmosphere of Uranus is composed primarily of molecular hydrogen, making up roughly 83% of its volume, followed by helium at approximately 15% and methane at about 2 to 2.5%. Trace amounts of other molecules, water, ammonia, hydrogen sulfide, acetylene, and more complex hydrocarbons formed by photochemical reactions have been detected in the upper atmosphere. The hydrogen sulfide was confirmed directly only in 2018 in a study published in Nature Astronomy using spectrographic data from the Gemini North Telescope. Its presence was expected from atmospheric models, but had not been observationally confirmed for decades. The temperature in the upper troposphere drops to approximately 49 Kelvin at the tropophause, the boundary between the troposphere below and the stratosphere above. 49 Kelvin is negative 224 degrees Celsius. This is the coldest atmospheric temperature recorded anywhere in the solar system, colder than the atmosphere of Neptune, which orbits roughly 1.5 billion kilometers farther from the Sun. The reason Uranus is colder than Neptune despite being closer to the Sun is one of the most discussed puzzles in planetary science, and it comes down to one unexpected fact. Uranus emits almost no internal heat. All of the other giant planets in the solar system, Jupiter, Saturn, and Neptune, emit significantly more heat than they receive from the Sun. This internal heat is a combination of residual thermal energy from their formation, when the gravitational collapse that built the planet released enormous amounts of energy, and ongoing heat from the slow gravitational contraction that continues as the planet's interior settles and compresses. Jupiter radiates approximately 1.9 times as much energy as it receives from the Sun. Saturn radiates about 2.3 times. Neptune radiates about 2.6 times. These numbers mean that these planets have warm interiors that actively drive atmospheric convection, pushing heat upward and releasing it into space. Uranus radiates less than 1.06 times what it receives. The excess is so small that it is barely distinguishable from zero. Whatever internal heat Uranus was born with, or whatever process should be releasing it now, is not reaching the outer atmosphere and escaping into space. The leading hypothesis involves a thermally stable layer deep in the interior, a region where the density gradient and the temperature gradient align in a way that suppresses convection. Rather than warm material rising toward the surface, it remains trapped beneath this stable layer, unable to mix upward. The heat generated in the deep interior, if any significant heat is being generated, stays locked inside. The outer layers, deprived of this internal energy source, cool to the temperatures they receive from the distant sun and no further. The result is an atmosphere that is cold, relatively uniform, and from the outside, almost featureless. Almost. As you move through the upper troposphere, you begin to detect structure. Not with your eyes. The visual appearance remains remarkably homogeneous, but the structure is there, in the patterns of wind, in the faint temperature variations, in the cloud features that satellite instruments have resolved in near-infrared and thermal wavelengths. The winds at the equator of Uranus are retrograde, blowing in the direction opposite to the planet's rotation. Measured wind speeds at low latitudes range from about 0 to 240 kilometers per hour in the retrograde direction. Moving toward higher latitudes, the wind direction reverses to prograde, aligned with the planet's rotation, and accelerates. At approximately 60 degrees latitude, wind speeds peak at measurements close to 900 kilometers per hour. These are extraordinary velocities. They are close to the speed of sound in dry air at sea level on Earth, and they are invisible to the eye from outside the planet because the atmosphere lacks the dramatic temperature contrasts and cloud top features that make wind systems visible on Jupiter and Saturn. In observations with the Hubble Space Telescope during the 1990s and early 2000s, and in more recent observations with the James Webb Space Telescope in its first years of operation, scientists have identified cloud features in Uranus's atmosphere at multiple altitude levels: bright methane ice clouds in the upper troposphere, banding structures that become more visible as the planet approaches its equinox, and a distinctive polar cap centered on the sunlit pole. The polar cap is a region of enhanced brightness observed in both reflected visible light and infrared emission. Its cause is not fully understood. It may involve photochemical haze particles that form differently at the pole due to the different angle and duration of sunlight exposure, or it may reflect differences in the vertical mixing of the atmosphere at high latitudes. In the JWST observations from 2023, the north polar cap of Uranus appeared with unusual clarity, a bright, roughly circular feature sitting at the top of the planet's visible disk, surrounded by a sharp transition to the dimmer mid-latitude regions. Within the polar cap, a bright inner polar cloud was visible, a concentrated feature at the very pole itself, possibly a persistent storm or circulation structure. Scientists are currently analyzing these observations to understand whether this inner feature is a permanent structure or a temporary phenomenon, and whether its formation is related to the approach of the 2028 Uranian equinox, the moment when the sun will cross the planet's equatorial plane and both poles will receive equal illumination for the first time in 42 years. You move deeper. The temperature rises as you descend below the tropopause into the troposphere. The pressure increases around you. At the 1 bar level, where atmospheric pressure equals 1 Earth atmosphere, the temperature is approximately 76 Kelvin. At 10 bars of pressure, roughly corresponding to a depth of several hundred kilometers below the cloud tops, temperatures reach around 320 Kelvin, about 47 degrees Celsius. At this level, models predict the presence of a water cloud layer, though direct observation of deep cloud layers on Uranus remains beyond current instrument capabilities. The atmosphere grows denser as you descend. The gas becomes less like a gas and more like something with resistance, with weight. The color, which was the pale blue-green of the methane-dominated upper layers, gradually gives way to a deeper, darker medium as the fraction of scattered light reaching your surroundings from above diminishes with depth. It is not dark in the way a cave is dark. It is dark in the way that deep water is dark, not absence of light, but attenuation of it, a deepening and softening until direction becomes ambiguous and distance loses meaning. And then, at some depth below the cloud layers, at pressures and temperatures that have no simple analog in any environment on the surface of Earth, the atmosphere ends. Not suddenly, not with a clear boundary, but somewhere in this deepening medium, the distinction between atmosphere and interior dissolves. The hydrogen and helium that dominated the upper layers become compressed to densities that make them indistinguishable in behavior from liquids. The water, ammonia, and methane that were minor trace components in the upper atmosphere become the dominant material in what lies below. You are entering the ice mantle. The term mantle, borrowed from the layered structure of rocky planets like Earth, refers here to the thick region between the outer gaseous envelope and the rocky core beneath. And the term ice is a classification inherited from the conditions at which water, ammonia, and methane solidify under low pressures and temperatures in the outer solar system, not a description of their physical state at the pressures and temperatures found here. Here, nothing is ice in any familiar sense. Water in the ice mantle of Uranus exists under pressures ranging from roughly 100,000 to several million times Earth's atmospheric pressure, and at temperatures ranging from thousands to tens of thousands of Kelvin. Under these conditions, the molecular structure of water undergoes transformations that were predicted theoretically long before they could be confirmed experimentally. The most remarkable of these transformations is a phase called superionic water. In liquid water, both the oxygen and the hydrogen atoms move freely, constantly breaking and reforming molecular bonds as the substance flows. In ordinary ice, the molecules are locked in place. The oxygen atoms form a crystalline lattice, and the hydrogen atoms sit in fixed positions, bonded between oxygen atoms. Superionic water is something different. The oxygen atoms lock into a rigid crystalline lattice. As in ordinary ice, they cannot move, but the hydrogen protons are released from their molecular bonds and become free to migrate through the lattice, moving from one oxygen lattice site to another. The result is a material that is crystalline and rigid like a solid, but through which electric charge flows like a metal conductor. The water inside this planet conducts electricity. The existence of superionic water was confirmed in laboratory experiments published in 2018 in the journal Nature Physics, conducted at the Lawrence Livermore National Laboratory using a technique called laser shock compression. Researchers compressed a thin film of water between diamond plates, then struck it with laser pulses of extraordinary intensity to generate a shock wave that drove the sample to pressures of up to 2 million atmospheres and temperatures of several thousand Kelvin, conditions comparable to those estimated to exist within the ice mantles of Uranus and Neptune. Measurements of the compressed water's properties confirmed the transition to a superionic state. The material became electrically conducting while simultaneously maintaining a solid-like structural order. The implications for Uranus extend beyond the existence of a strange phase of water. The magnetic field of Uranus is generated somewhere in this region, in the electrically conducting ice mantle, rather than in a metallic liquid outer core, the way Earth's magnetic field is generated. And the field that results from this deep mantle generation is unlike any other planetary magnetic field in the solar system. Earth's magnetic field is roughly aligned with its rotational axis. The North Magnetic Pole and the geographic North Pole differ by only about 11 degrees. Jupiter's field is offset by about 10 degrees. Saturn's field is nearly perfectly aligned with its rotation axis. Uranus's magnetic field is offset from its rotational axis by 59 degrees. Furthermore, the center of the magnetic field, the point around which the dipole is organized, is not at the center of the planet. It is displaced from the geometric center by roughly 30% of the planet's radius, shifted toward the southern hemisphere. A magnetic field whose axis is 59 degrees from the rotation axis, centered nowhere near the planet's core, generated in a region of superionic water and ionic fluid rather than in a metallic liquid. It is a magnetic environment that produces a magnetosphere unlike any other in the solar system. As Uranus rotates, once every 17 hours and 14 minutes, its offset, tilted magnetic field sweeps through space in a wobbling asymmetric pattern. On one side of the planet, the magnetic field lines are compressed by the solar wind. On the other side, they are stretched into a long magnetotail that extends millions of kilometers behind the planet in the direction away from the sun. As the planet rotates, this configuration changes dramatically, the magnetosphere breathing in and out, twisting and untwisting, in a complex pattern that the single brief pass of Voyager 2 in 1986 only began to document. The detailed structure of the Uranian magnetosphere remains poorly understood. Modeling it requires understanding the specific geometry of the current generating region inside the planet, the shape and connectivity structure of the superionic mantle, and this is still a matter of active research and ongoing theoretical refinement. You remain still in the ice mantle. The pressure is immense in every direction. The material around you is dense and conductive and hot, thousands of Kelvin at this depth, far hotter than any temperature at the surface of the planet. The heat bottled up by the insulating stable layer somewhere above you, unable to convect upward, unable to escape. The planet rotates slowly around you. Its magnetic field sweeps outward and inward in its asymmetric, wobbling pattern. Far above, in the pale blue-green atmosphere, the winds move at 900 kilometers per hour through what looks, from the outside, like perfect silence. In, out. You are at the center of one of the least understood planets in the solar system, a world that has been visited exactly once, observed from Earth for nearly 2.5 centuries, modeled and theorized and argued over in papers and conference rooms and telescope allocation proposals, and which still holds more unknown than known in its deep interior. The core lies beneath you, believed to be a rocky, icy mixture, roughly the mass of Earth, compressed to densities and temperatures beyond anything that exists naturally on the surface of our planet. It has never been directly observed. No probe has reached it. No signal from the surface of Earth can penetrate to it. It sits at the geometric center of a world that has been rolling through the outer solar system for 4.5 billion years, silent and unreachable, holding its heat. The silence here is not empty. It is the silence of material under enormous pressure, of protons moving through crystalline oxygen lattices in every direction, of heat trapped and circulating in patterns too deep and too slow to measure with any instrument yet built, of a magnetic field being generated in real time by processes that are only now beginning to be confirmed in Earth-based laboratories. This is what the inside of an ice giant feels like. Not cold, not simple, not empty, but compressed, conducting, ancient, and strange. Far above you, the pale atmosphere continues its quiet rotation, and the 27 moons of Uranus move in their tilted orbits around the planet, some icy, some cratered, some fractured, some holding geological features so extreme that they belong in a separate category from anything else in the solar system. The diamonds have not yet begun to fall in this part of the story. That happens higher in the region above you, in the deep atmosphere where carbon from methane molecules is stripped of its hydrogen bonds and forced, under the right conditions of pressure and temperature, into the tetrahedral structure of crystalline carbon. That is where this story goes next. But for now, you remain here, in the mantle, in the slow, conductive silence of a world that spins on its side and keeps almost everything it knows to itself. The pressure holds you gently from every direction. The temperature is thousands of degrees, and you feel none of it. The planet rotates, and you stay very still. The story of Uranus as a known object, a catalogued, named, studied planet, begins on the night of March the 13th, 1781, in the English city of Bath. William Herschel, a musician by profession who had built one of the finest reflecting telescopes in the world in his spare time, was conducting a systematic survey of the sky. He had a method, moving methodically from field to field, measuring the positions and apparent sizes of stars, comparing what he saw to existing catalogs. He was looking for double stars. He was not looking for a planet. What he found in the constellation Gemini was an object that appeared larger than the surrounding stars and seemed, over successive nights of observation, to move against the fixed background of the stellar field. He initially cataloged it as a comet, the most natural category for a moving object of uncertain nature in an 18th century sky survey. But the object moved too slowly, followed too nearly circular a path, and showed a disk shape under magnification rather than the diffuse glow of a comet's coma. After several months of observation and correspondence with other astronomers, the conclusion was unavoidable. This was a planet moving in a nearly circular orbit, well beyond Saturn. It was the first planet to be discovered in recorded history. Every planet known before 1781, Mercury, Venus, Mars, Jupiter, Saturn, had been known since antiquity. They were visible to the naked eye and had been tracked and named and incorporated into mythology and calendars for thousands of years. Uranus was the first planet that required a telescope to find, the first planet whose existence required technology to reveal. The discovery immediately expanded the known scale of the solar system by nearly doubling the distance to its outer boundary. Saturn's average orbital radius is roughly 9.5 astronomical units, 9.5 times the distance from Earth to the Sun. Uranus orbits at an average of 19.2 astronomical units. The outer solar system was suddenly twice as large as it had been the day before, and the planet itself resisted easy understanding from the beginning. Early calculations of its orbit showed peculiarities. The predicted position based on Newtonian gravitational mechanics did not quite match the observed position over time. The discrepancy was small but consistent and grew over decades of observation. By the middle of the 19th century, the discrepancy was large enough that two mathematicians, Urbain Le Verrier in France and John Couch Adams in England, working independently, proposed the same explanation: an unknown planet beyond Uranus whose gravitational influence was perturbing its orbit. They calculated where such a planet would need to be. In 1846, astronomers pointed their telescopes to those coordinates and found Neptune. Uranus, simply by existing and moving slightly wrong, led directly to the discovery of another entire planet. For nearly 2 centuries after its discovery, Uranus remained a distant, featureless disk in the world's telescopes. Its atmosphere showed no structure that the instruments of the time could resolve. Its rings were invisible, too dark and too narrow to be detected. Its moons were discovered slowly, one by one, Titania and Oberon by Herschel himself in 1787, Ariel and Umbriel by William Lassell in 1851, and Miranda by Gerard Kuiper in 1948. Each discovery added a small new element to the picture of a system that remained, in its large-scale structure and composition, almost completely unknown. Then came Voyager 2. The Voyager 2 spacecraft was launched on August the 20th, 1977. It was the second of the 2 Voyager probes launched that year. Voyager 1 was launched 16 days later, but on a faster trajectory that took it past Jupiter and Saturn, ahead of Voyager 2. Both probes were designed to take advantage of a rare planetary alignment, a configuration that occurs only once every approximately 175 years, in which Jupiter, Saturn, Uranus, and Neptune are positioned so that a spacecraft could use the gravity of each planet to accelerate and redirect toward the next, a technique called a gravity assist. Voyager 2 flew past Jupiter in July of 1979, Saturn in August of 1981, and then began the long journey outward to Uranus. The transit from Saturn to Uranus took 4.5 years. During that time, the spacecraft was in interplanetary space, traveling without any significant maneuvers, its instruments pointing at various targets as opportunities arose, its antennas periodically communicating with Earth across distances that grew to nearly 3 billion kilometers. On January the 24th, 1986, Voyager 2 reached closest approach to Uranus, passing within 81,500 kilometers of the planet's cloud tops, closer than any spacecraft has ever been before or since. The encounter lasted approximately 6 hours at closest approach, though data collection began weeks before and continued weeks after. In those 6 hours near the planet, the spacecraft's cameras captured the first close-up images of Uranus and its moons. Its magnetometers measured the magnetic field, Its radio science instruments probed the atmosphere, and its plasma and particle detectors characterized the space environment around the planet. The data returned by Voyager 2 in 1986 transformed what was known about Uranus from speculation and distant observation into measurement before the flyby. 5 known moons, no confirmed rings, no direct measurement of the magnetic field, no atmospheric data below the cloud tops. After 10 new moons discovered, 11 rings confirmed, the magnetic field measured and found to be wildly offset from the rotation axis, and atmospheric data that revealed the wind structure and temperature profile of the upper troposphere. And then the spacecraft continued on toward Neptune, and no one went back. The scientific community has debated and proposed and redesigned missions to Uranus for decades. In 2022, the National Academies of Sciences, Engineering, and Medicine published a Planetary Science Decadal Survey, the document that guides NASA's science priorities for a 10-year period, that listed an Uranus orbiter and atmospheric probe as the highest priority large mission for the coming decade. The proposed mission would carry a spacecraft into orbit around Uranus, allowing years of continuous observation rather than a single flyby, and would release a probe into the atmosphere to directly measure the composition and structure of the deep atmospheric layers that Voyager 2 could only infer from a distance. As of the mid-2020s, the mission remains in pre-formulation, studied, designed in concept, prioritized, but not yet funded or officially approved. The earliest realistic launch window is in the early 2030s, with an arrival at Uranus taking approximately 12 to 13 years from launch, depending on the trajectory chosen. The planet continues its patient rolling in the meantime. You have been in the ice mantle for some time now. The conductive material surrounds you with its enormous pressure and its thousands of Kelvin of trapped heat. The wobbling magnetic field rotates around you as the planet turns, sweeping its offset dipole through the magnetosphere above in its distinctive asymmetric pattern. Somewhere in the region above you, in the transition zone between the deep atmosphere and the upper mantle, at pressures of perhaps 1 to 10 million atmospheres and temperatures of several thousand Kelvin, something remarkable is happening to the methane. Methane is a molecule composed of 1 carbon atom bonded to 4 hydrogen atoms. In the upper atmosphere of Uranus, methane exists in its familiar molecular form, the same molecule that makes up natural gas on Earth, that forms in the digestive systems of livestock, that is released from thawing permafrost and from the depths of ocean sediments. At these temperatures and these altitudes, methane behaves like methane. But as methane descends into the deep atmosphere and encounters rising pressures and temperatures, the molecule destabilizes. The carbon-hydrogen bonds are strong, but they are not infinitely strong. Under sufficient compression, under temperatures high enough to provide the thermal energy needed to break those bonds, the methane molecule dissociates. The hydrogen atoms separate from the carbon, and the carbon atoms, now free, find themselves in an environment of extreme pressure. Under the right conditions of pressure and temperature, the conditions that exist in the deep interiors of ice giants, free carbon atoms do not remain in solution or form complex organic molecules. Instead, they are compressed into the most stable form available under those conditions. They form diamonds. The process was first proposed theoretically in the 1970s and 1980s, based on high-pressure physics calculations showing that carbon under conditions of millions of atmospheres of pressure would adopt the diamond crystal structure as its lowest energy configuration. The experimental confirmation came in 2017 in a study published in Nature Astronomy by a team of researchers at SLAC National Accelerator Laboratory and other institutions. Using a powerful optical laser to drive a polystyrene sample, a carbon-hydrogen polymer, to pressures of up to 150 gigapascals, comparable to pressures found several thousand kilometers deep inside Uranus. The researchers observed the formation of nanometer-scale diamond crystals in real time using an X-ray free electron laser. The results were unambiguous. At the right pressures and temperatures, carbon from hydrocarbon molecules separates and crystallizes into diamond. And inside Uranus, those pressures and temperatures exist over an enormous volume of the planet's interior. The diamonds that form in this region do not stay where they form. Diamond is denser than the surrounding fluid. Its density of approximately 3.5 grams per cubic centimeter exceeds the density of the surrounding ionic fluid under these conditions, and so the diamond crystals, once formed, begin to sink slowly against the resistance of the dense fluid medium. They fall toward the center of the planet. The estimated terminal velocity of diamond crystals falling through the deep interior of an ice giant, the velocity at which the gravitational force pulling them downward balances the drag force of the surrounding medium, is believed to be centimeters per second, extremely slow by any everyday measure, but persistent, continuous, ongoing for billions of years. Over geological timescales, the cumulative effect of this slow rain of diamonds falling toward the center is a diamond-enriched region in the deep interior, a layer or accumulation of diamond material that may have been building for billions of years since the planet formed and its interior first reached the pressures and temperatures required for this process to operate. No instrument has confirmed this directly. The diamonds inside Uranus are inaccessible, buried under pressures that would destroy any probe yet conceivable, in a region that has never been visited and that no currently planned mission will reach. Their existence is inferred from the physics of carbon under pressure, from laboratory experiments that replicate the relevant conditions, and from theoretical models of ice giant interiors. But the physics is solid, the experiments are reproducible, the inference is well supported. Inside the planet, rotating slowly around you, diamonds are falling. They have been falling since shortly after the solar system formed, when the planet's interior first compressed to the conditions required for the process to begin. They fall at a few centimeters per second through a medium of superionic water and ionic ammonia and methane. They accumulate somewhere in the deep interior, in a region that will never be directly observed by any instrument currently conceivable. The planet holds this inside itself, quietly, while its pale blue-green atmosphere turns slowly in the sunlight that reaches here, at 360 times less intensity than it reaches Earth. In, out, you remain very still in the ice mantle. The pressure is constant, the temperature is thousands of Kelvin, the magnetic field wobbles through its rotation above you in its asymmetric, tilted pattern. Far below, the rocky core sits at the center of everything, ancient and compressed and silent. And somewhere in the region between where you are and where the atmosphere begins above you, carbon atoms are separating from their hydrogen bonds, crystallizing and beginning their slow fall toward the center of the world. This is the interior of Uranus. This is what an ice giant holds inside itself, 4.5 billion years after it formed. Strange water, strange magnetism, strange carbon, and a silence that has been interrupted only once, for 6 hours, by a spacecraft named Voyager 2 that flew past in January of 1986 and kept going. The planet continues its patient rotation, 17 hours and 14 minutes per turn, rolling on its side, carrying its secrets inward, raining diamonds in the dark. The carbon was always there. It arrived with the planet itself, locked inside methane molecules that formed in the cold outer regions of the solar nebula, the disk of gas and dust that surrounded the young sun 4.5 billion years ago. Methane is a simple molecule, one carbon atom bonded to 4 hydrogen atoms, stable under the low pressure, low temperature conditions of interstellar space and the outer solar system. In the atmosphere of Uranus, in the upper troposphere where pressures are measured in fractions of a bar and temperatures sit near 50 Kelvin, methane behaves exactly as it does anywhere else in the cold outer solar system. It floats, it absorbs red light, it gives the planet its color. But the atmosphere of Uranus is not only its upper layers. Below the cloud tops, below the methane ice crystals that form at altitude, below the hydrogen sulfide clouds that models predict at greater depths, below the level where any instrument has yet directly probed, the atmosphere deepens into pressure regimes that transform everything. The pressure increases with depth in any planetary atmosphere, the weight of the gas above compressing the gas below. In the upper troposphere, pressures are fractions of a bar. At tens of bars, the atmosphere is already denser than the air at Earth's surface by orders of magnitude. At hundreds of bars, the distinction between gas and liquid begins to blur, and somewhere in the region beyond that, at pressures of hundreds of thousands to millions of atmospheres, in the transition zone between deep atmosphere and ice mantle, the methane molecule encounters conditions it cannot survive intact. The bonds break. Not explosively, not all at once, but under the combined assault of extreme pressure and temperature, temperatures of several thousand Kelvin in this region, pressures of 1 to 10 million atmospheres, the carbon-hydrogen bonds in methane reach their breaking threshold. The hydrogen atoms separate. They migrate into the surrounding ionic fluid, joining the complex mixture of free protons and molecular hydrogen that fills this region. And the carbon atoms, 4 of them for every methane molecule that dissociates, are left alone in an environment of crushing pressure. A carbon atom under 1 million atmospheres of pressure is not a carbon atom in a comfortable situation. Carbon at low pressures can arrange itself in many ways. Graphite, the carbon of pencil lead, is a structure of flat hexagonal sheets, weakly bonded to each other, that forms under conditions of low pressure. Fullerenes, nanotubes, amorphous carbon, many structural forms are accessible at low pressures. But at extremely high pressures, the calculation changes. The thermodynamically stable form of carbon at pressures above roughly 100,000 atmospheres, and at the temperatures found in the deep interior of Uranus, is the diamond crystal structure. In diamond, each carbon atom is bonded to 4 neighboring carbon atoms in a tetrahedral arrangement, 1 atom at the center of a tetrahedron, 4 atoms at its corners, each of those 4 also bonded to 3 more in the same arrangement, extending outward in all directions. This structure is extraordinarily compact and mechanically stable. It produces the hardest naturally occurring substance on Earth. and it is the form that carbon spontaneously adopts when compressed to the pressures found inside ice giants. The carbon crystallizes, it becomes diamond, and then it begins to fall. The experimental confirmation of this process came in 2017 at the SLAC National Accelerator Laboratory in California. A team of researchers, led by Dominic Krauss of the Helmholtz-Zentrum Dresden-Rosendorf, designed an experiment to replicate the pressure and temperature conditions found deep inside Uranus and Neptune. They chose polystyrene as their sample material, a polymer with the chemical formula CaHa-thin, a chain of carbon and hydrogen atoms in roughly the same ratio as the hydrocarbon mixture expected in the deep interiors of ice giants. They placed a thin film of polystyrene in the path of a powerful optical laser at the SLAC facility's Matter in Extreme Conditions instrument. The laser pulse, lasting only about a nanosecond, but carrying enormous energy density, drove a shock wave through the polystyrene sample, compressing it to pressures of roughly 150 gigapascals, approximately 1.5 million atmospheres, while simultaneously heating it to temperatures of several thousand Kelvin. To observe what happened during this compression, the team used a separate X-ray pulse from the SLAC X-ray free electron laser, the most powerful X-ray laser in the world, timed to arrive at the sample during the peak of compression. X-rays scatter off the crystal structure of materials in patterns that are specific to the arrangement of atoms, a technique called X-ray diffraction, and the scattering pattern observed during the compression showed unmistakably the signature of diamond crystal structure forming in the compressed polystyrene. The carbon atoms, stripped from their hydrogen bonds by the shock, had crystallized into diamond in nanoseconds. The experiment also provided the first direct evidence, beyond theoretical prediction, that these diamond crystals would sink through the surrounding fluid rather than dissolve or disperse. The density of diamond, approximately 3.5 grams per cubic centimeter, exceeds the density of the surrounding ionic fluid under these conditions, meaning that gravity would pull the diamond crystals downward through the fluid medium. A subsequent experiment, published in 2022 in Science Advances by many of the same researchers, extended the work to conditions even closer to those inside Neptune and Uranus, higher pressures, and a sample material that included oxygen atoms alongside the carbon and hydrogen, and found that the presence of oxygen from water molecules actually enhanced the diamond formation process. You are in the deep atmosphere now, above the ice mantle where you rested before, in the region where the pressure is building toward the threshold of diamond formation. The material around you is dense and hot. The hydrogen and helium of the upper atmosphere are far above. Here, the dominant molecules are water, ammonia, and methane in their compressed, partially dissociated forms. The temperature is several thousand Kelvin. The pressure, measured in the millions of atmospheres, pushes against every surface in every direction. And in the fluid around you, the methane molecules are coming apart. You cannot see this process with eyes. It is happening at the molecular scale, at speeds far beyond perception, but it is happening everywhere, continuously, in the enormous volume of the planet's deep atmosphere. Carbon atoms are separating from their hydrogen companions and being driven by the pressure that fills this region into the diamond crystal structure. Small at first, nanometer scale crystals, too small to see, too small to feel, but real in the way that all things confirmed by X-ray diffraction are real. The crystals grow as more carbon atoms join the expanding lattice. Nanometers become micrometers, the diamonds grow. and then they begin to fall. The fall is slow, the surrounding fluid is dense, far denser than any fluid on Earth's surface, and the viscosity and drag it exerts on a falling crystal are significant. Estimates of the terminal velocity of diamond crystals falling through the deep interior of an ice giant range from a few millimeters per second to a few centimeters per second, depending on the size of the crystal and the properties of the surrounding medium at that depth. A centimeter per second. In 1 year, a falling diamond crystal covers approximately 315 kilometers. In 1 million years, it covers 315 million kilometers, comparable to the distance from Earth to the Sun. The planet's deep interior, from the base of the atmosphere to the rocky core, spans roughly 20,000 kilometers. A diamond crystal falling at 1 centimeter per second would traverse that distance in roughly 20 million seconds, about 2/3 of a year. But the crystals do not all form at the same depth. They do not all fall in straight lines. The deep interior of Uranus is not a static medium. It is convecting, circulating in slow patterns, driven by the thermal gradients and compositional gradients within the planet. A diamond crystal forming in the deep atmosphere may be carried by convective currents before it falls far enough to accumulate with others. The actual distribution of diamonds within the planet's interior is a complex function of fluid dynamics, thermodynamics, and the specific density structure of the interior, a structure that cannot yet be observed directly. What can be said is this: the process has been operating for billions of years. Uranus is approximately 4.5 billion years old, formed from the solar nebula at roughly the same time as every other planet in the solar system in the first few tens of millions of years after the Sun ignited. For most of that 4.5 billion years, since the planet first compressed to the pressures and temperatures required for diamond formation, carbon from dissociated methane has been crystallizing and falling toward the center of the planet. The cumulative effect over geological timescales is an interior that has been modified by this ongoing process. Some models suggest that the deep interior of ice giants like Uranus may have a diamond-enriched layer, a region where the accumulated diamonds of billions of years have concentrated, forming a layer or region of diamond material at depth. Whether this layer is a distinct shell, a diffuse concentration, or something else entirely is not known. The resolution of current observational and modeling techniques does not reach this deep. Inside this planet, something that began as swamp gas has become diamond, and it is still happening right now. You watch the crystals form in the fluid around you, not with eyes, but with something like awareness. They are small. They are falling in every direction, following the complex geometry of the fluid currents that move through this region. Some fall faster than others. Some are carried sideways by circulation before gravity reasserts itself and pulls them downward. The planet makes no sound in the process of making diamonds. There is no crystallization event audible here, no ping of crystal formation, no rush of falling material. The process is distributed over an enormous volume, operating at molecular scales, silent and continuous. The only sound, if anything could be called a sound at this depth and pressure, would be the deep, slow movement of the surrounding fluid, a movement so low in frequency and so vast in scale that it would be felt more than heard. In, out. The diamonds fall. They fall through the region where you stand, or hover, or exist in whatever sense you exist here, and continue downward into the ice mantle below, into the superionic water and ionic ammonia, into the increasing pressure and temperature of the planet's deep interior, toward a rocky core that sits at the center of the planet, compressed and ancient and unreachable. And they will continue to fall for as long as Uranus exists, for billions of years more if the solar system remains stable, if the sun does not expand and disrupt the outer planets before their time, if the gentle physics of carbon under pressure continues to operate in the deep interior of this sideways world. The chemistry of a planet is not a fixed thing. It evolves slowly, too slowly for any human timescale to perceive, but continuously. The Uranus that exists right now is not exactly the Uranus of a billion years ago. The distribution of carbon in its interior has shifted. The ratio of methane to other compounds in different layers has changed as methane is consumed and diamonds accumulate. The planet is processing itself chemically at a rate of grams or kilograms of diamond per second, a rate that is negligible on any human timescale, but immense on a geological one. You remain still, surrounded by the slow crystallization of diamond in the dense, hot fluid of the deep atmosphere. Above you, more than 20,000 kilometers of atmosphere and ice mantle separate you from the pale blue-green surface of the planet. Far below, the rocky core waits at pressures of 6 to 8 million atmospheres, at temperatures that may exceed 20,000 Kelvin, and all around you, at the pressures and temperatures of this particular depth, carbon is doing what carbon does under these conditions. It is becoming diamond. It is falling. It has been doing this since before the Earth had continents. The enormity of that timeline settles around you like the pressure of the planet itself, not crushing but present, unmistakable, insisting on its own reality. 4.5 billion years. Diamonds falling through the dark interior of a planet that no human has ever visited in person, that only one machine has ever approached, that sits 2.5 billion kilometers beyond where the sun's warmth becomes meaningful. And it is not an exceptional planet. Across the galaxy, in planetary systems around other stars, in the systems discovered in the past 3 decades by the Kepler Space Telescope and the TESS mission and ground-based radial velocity surveys, planets the size of Uranus and Neptune are extraordinarily common. They appear to be among the most frequent outcomes of planetary formation. In the known exoplanet population, the category of planets between roughly 2 and 4 times Earth's radius, a category that includes Uranus at approximately 4 Earth radii, is one of the most populated in the observed distribution. Scientists call them mini-Neptunes, or sub-Neptunes, or simply ice giants, depending on the context. Many of them likely have the same internal structure as Uranus and Neptune, a compressed volatile mantle, a rocky core, a hydrogen-helium envelope. Many of them likely have the same chemistry in their deep interiors, dissociating methane, crystallizing carbon, falling diamonds. The diamond rain inside Uranus is not a curiosity unique to this one planet. It is likely a common feature of a class of worlds that may be the most abundant type of planet in the galaxy. The galaxy may be full of worlds where it rains diamond. You hold that thought in the dense, hot quiet of the deep atmosphere. Above you, far above, the pale surface of the planet rotates in the weak sunlight of the outer solar system. The rings orbit in their tilted plane. The 27 moons move in their distant paths. And somewhere in between, in this deep, dark, pressurized interior, The diamonds continue their slow and patient fall toward the center of a world that has been making them quietly for longer than the Earth has existed. The temperature is still thousands of Kelvin. The pressure is still millions of atmospheres. Nothing about your surroundings suggests that anything unusual is happening. The process that is making diamonds around you is indistinguishable to any available sense from any other aspect of this deep, featureless medium. But it is happening. It has always been happening. You let yourself drift upward, slowly, through the layers of increasing cold and decreasing pressure, back through the ice mantle, back into the deep troposphere, back through the cloud layers, back into the pale blue-green of the upper atmosphere. The temperature drops, the pressure falls, the density around you decreases. The color of the light changes, shifting from nothing to something, from the total absence of illumination in the deep interior to a faint diffuse glow from the sunlight scattered through the methane-rich upper layers. You emerge into the atmosphere. And here in the upper troposphere of Uranus, as the planet rolls through its orbit, you become aware of something you could not perceive from inside. The planet is not behaving the same everywhere at once. Uranus has seasons, but not the mild, predictable seasons of a planet with a modest axial tilt. The seasons of Uranus are extreme in a way that has no precedent among the other planets in the solar system. The season that is coming, or that has recently changed, depending on when in the 84-year orbit you are observing, is unlike anything that occurs on Earth. To understand it fully, you need to step back and look at the planet as a whole, from outside, from a position where you can see both poles at once, and understand what the axial tilt of 97.77 degrees actually means for the distribution of sunlight across the planet's surface and atmosphere over the course of an entire Uranian year. Uranus orbits the Sun in a nearly circular path, with an eccentricity of only 0.046, meaning its distance from the Sun varies by less than 5% between its closest and farthest points. Over the course of its 84-year orbit, the total amount of sunlight reaching the planet changes very little due to orbital eccentricity, but the distribution of that sunlight across the planet's latitudes changes enormously due to the axial tilt. At one point in the Uranian year, when the North Pole is aimed most directly at the Sun, the North Polar region of the planet receives continuous sunlight. The Sun moves in a slow circle around the sky, never setting, just cycling in altitude through each 17-hour rotation. Below the polar region, the lower latitudes see a sun that rises and sets, but that spends more time above the horizon the closer you are to the pole. At the equator, the sun rises almost perpendicular to the horizon and sets relatively quickly. In the southern hemisphere, pointed away from the sun, the conditions are reversed. The south polar region is in continuous darkness, and the lower southern latitudes experience a sun that barely rises above the horizon. This is the summer solstice of Uranus's northern hemisphere. For 42 years, the North Pole has been in continuous daylight. For 42 years, the South Pole has been in continuous night. Then the planet continues its orbit, and the relationship between the poles and the sun gradually changes. The North Pole moves away from direct sunlight. The equatorial regions experience a transitional period where the sun crosses the equator, a Uranian equinox. And eventually, the South Pole points toward the sun, and the pattern reverses. 42 years of southern summer, 42 years of northern winter. The most recent southern summer solstice on Uranus occurred in 1986, the same year Voyager 2 flew past, when the South Pole was aimed almost directly at the Sun. The subsequent equinox occurred in 2007, when the Sun crossed the Uranian equator and illuminated both poles equally for the first time in 42 years. Since 2007, the Northern Hemisphere has been moving into its summer, with the North Pole receiving progressively more direct sunlight. The next northern summer solstice, when the North Pole will be most directly aimed at the Sun, is expected around 2028. Right now, you are watching the planet approach that solstice. The North Pole is becoming one of the most sunlit places in the entire solar system's outer regions, not in absolute terms, since the sunlight here is always far weaker than at Earth, but in terms of the duration of sunlight received at a single location. The North Polar region of Uranus is currently experiencing the longest continuous period of direct sunlight it will receive in its entire 84-year cycle. And what does this produce? Not warmth in any simple sense. The amount of solar energy reaching Uranus at this distance is too low to heat the polar atmosphere significantly. Even 42 years of continuous sunlight raises the temperature of the polar atmosphere by only modest amounts compared to the extreme cold of the surrounding planet. But the difference in illumination creates atmospheric circulation. It creates chemistry. It creates the polar cap that the James Webb Space Telescope has been observing in its early years of operation, the bright, reflective region centered on the North Pole that stands out clearly in infrared observations. The polar cap forms because the extended sunlight drives photochemical reactions in the atmosphere. Ultraviolet light from the sun breaks apart molecules in the upper atmosphere, producing reactive chemical fragments that recombine into complex organic molecules. Hydrocarbons with more carbon atoms than methane, compounds like ethane, acetylene, and diacetylene that form a haze layer at altitude. This photochemical haze scatters sunlight more efficiently than the surrounding atmosphere, making the polar region appear brighter in reflected light. 42 years of sunlight, making chemistry happen in the frozen sky. The polar vortex, a pattern of circulation in the atmosphere that organizes around the pole during the long summer, also contributes to the cap's structure. As the pole receives continuous sunlight, the atmosphere above it develops a distinct circulation pattern, with descending air at the pole itself and rising air at the margins of the sunlit region. This circulation concentrates the photochemical haze near the pole and maintains the sharp boundary observed at the edges of the polar cap. You move toward the North Pole of Uranus, following the atmospheric circulation. The high latitudes of Uranus are strange in a way that is difficult to describe using the vocabulary of Earth weather. There is no day-night cycle here, not in any sense that a human body would recognize. The sun simply moves in slow circles above the horizon, completing one circuit every 17 hours as the planet rotates. It does not set, it does not rise. It simply traces its path in the sky, slightly higher and slightly lower depending on the season within the season, the sub-seasonal variation caused by the daily rotation. Below your feet, below the atmosphere you are moving through, there is no solid surface. There is no ground to land on, no rock to stand on, no boundary where the atmosphere gives way to something firmer. The atmosphere simply deepens and thickens as you descend, becoming liquid-like in behavior before transitioning into the ice mantle. If you descended far enough, you would eventually reach the rocky core, but there is no surface in the way a terrestrial planet has a surface. You are suspended in an atmosphere that has been receiving sunlight continuously for decades. The cloud features here, at high northern latitudes, are more active than the near-featureless equatorial regions. Hubble Space Telescope observations from the 2010s and 2020s recorded multiple discrete cloud features at mid to high latitudes in the northern hemisphere, bright, compact clouds that moved with the local wind flow, changed shape over days to weeks, and occasionally merged or dissipated. In 2023, a particularly large and bright storm feature appeared in the northern hemisphere, visible even in images taken by amateur astronomers with sufficiently large telescopes. The storm was bright enough in near-infrared light to stand out clearly against the surrounding atmosphere. The seasonal forcing is real. As the North Pole moves closer to the sun's direct illumination, the atmospheric dynamics are changing. The planet is not the same as it was 42 years ago. Its atmosphere is responding to the changing geometry of sunlight, slowly, over decades, in ways that scientists are only beginning to observe with sufficient continuity to characterize. The Hubble Space Telescope has been observing Uranus periodically since its launch in 1990. The JWST, launched in December of 2021 and now operating in its science phase, has begun providing observations of Uranus in wavelengths, particularly mid-infrared, that were not available to Hubble. The combination of these observatories, along with ground-based telescopes, is building a picture of how the Uranian atmosphere changes over the course of a season. But a full Uranian year is 84 Earth years. No single observatory has operated long enough to observe a complete cycle. Hubble has observed roughly 40 years of the cycle. No observations of comparable quality exist from before the space age. The full picture of how Uranus's atmosphere evolves through a complete year, from one solstice to the next and back, will require generations of astronomers and decades more of observation. You drift south from the North Pole, moving toward the equatorial region, where the transition between the sunlit northern hemisphere and the currently darker southern hemisphere is taking place. The sun, small, bright, not warm, hangs in the sky above the northern horizon from where you now are. Toward the south, the sky is darker. The southern hemisphere, in its slow transition from the 42 years of summer it enjoyed ending around 2007, is settling into its long northern winter, the sun now barely reaching above the southern horizon, spending most of each rotation below the equatorial plane. The atmosphere here at the equatorial latitudes is different from both poles. The wind flow is retrograde, blowing opposite to the planet's rotation, and relatively featureless, but there are clouds. Observations with adaptive optics on large ground-based telescopes have recorded banded structures at Uranian mid-latitudes, regions of slightly brighter cloud in the upper troposphere, corresponding to regions of upwelling atmosphere where methane ice clouds form at altitude. The equatorial and mid-latitude atmosphere will become more active as the planet approaches its 2028 solstice. Historical observations comparing images from the years around the 2007 equinox to earlier and later periods suggest that the atmosphere near the equinox is more dynamic, with more visible cloud features and greater contrast between atmospheric bands. The increase in activity is thought to be related to the changing distribution of solar heating as the sun crosses the equatorial plane and the global circulation pattern adjusts. In. The planet breathes in its own slow way, its atmospheric circulation responding to a 42-year cycle of sunlight and shadow, its chemistry changing over decades, its polar caps forming and dissipating over timescales that span human lifetimes. Out. You have been in the atmosphere for a long time now. The pale blue-green light filters from above. The temperature is tens of Kelvin below the coldest recorded temperature at Earth's surface. The wind at mid-latitudes moves at hundreds of kilometers per hour, and yet, if you were watching from the outside, you would see almost nothing of it, almost no visible structure, almost no obvious motion. The strangeness of Uranus is this: so much is happening, and so little of it is visible. Below you, deep in the interior, diamonds are falling through hot, pressurized fluid. Above you, the polar cap accumulates its photochemical haze in the continuous sunlight of a 42-year summer. Around you, the winds carry their enormous velocities in near silence and near invisibility. And somewhere in the history of this planet, 4.5 billion years ago, something massive struck it with enough force to knock its entire rotational axis 97 degrees from vertical, creating all of these extremes all at once and setting them in motion for the remainder of the solar system's existence. The seasons that last decades, the diamonds falling in the dark, the coldest atmosphere in the solar system, all of it traceable to one ancient impact, a collision so large and so long ago that no evidence of it remains except the tilt itself, carried forward through 4.5 billion years of continued rolling, continued falling, continued silence. The planet does not mark the anniversary of its great collision. It does not carry visible scars from it. It carries only the consequences: an axial tilt, an offset magnetic field, a set of extreme seasons, a chemistry that makes diamonds. You settle into the atmosphere as the planet rotates. The sun traces its low, slow circle in the sky. The northern hemisphere moves toward its long solstice. The diamonds fall. The rotation of Uranus takes 17 hours and 14 minutes. In that time, one Uranian day, the north pole of the planet completes a full circle relative to the sun. The sun traces its path in the polar sky, always above the horizon, always present, moving at a rate so slow that a human observer would need several hours of watching to notice its movement. This is not how seasons work on Earth. On Earth, the axial tilt of 23.5 degrees means that at the summer solstice, the northern hemisphere is tilted toward the sun. The days are longer. At the Arctic Circle, the sun stays above the horizon for 24 hours on the solstice day, but this effect lasts only a few days around the solstice at extreme latitudes, and at lower latitudes it produces the familiar variation between summer and winter day length. The seasons are annual. A full cycle from summer to winter and back takes one Earth year. On Uranus, the effect is not annual, it is orbital. The tilt is not 23 degrees, it is 97. The poles do not tilt toward the sun for a week or a month. They tilt toward the sun for 42 years, and then they point away for 42 years. And there is no meaningful concept of a day-night cycle at the pole during that entire 42-year period. Only the sun, tracing its circle, never setting for decades. The implications for atmospheric chemistry are profound. Photochemical reactions in the upper atmosphere of Uranus require ultraviolet light from the sun to drive them. The rate of those reactions, the rate at which complex organic molecules form from simpler precursors, the rate at which the photochemical haze is produced, depends directly on the intensity and duration of ultraviolet exposure. At the sunlit pole, during the 42-year summer, the rate of photochemical production is continuously high. The haze accumulates, the polar cap brightens. At the opposite pole, in continuous night, no photochemical reactions are being driven. The haze that accumulated during the previous summer, now without ultraviolet light to regenerate it, gradually settles or disperses. The polar cap at the winter pole, if it forms at all, is a ghost of its summer counterpart. The boundary between these two regimes, between the 42-year summer and the 42-year winter, is not a sharp line. It is a transition zone, a band of latitudes around the equatorial plane, where the sun's elevation above the horizon transitions from always positive in the summer hemisphere to always negative in the winter hemisphere, with the equatorial latitudes experiencing something in between, a sun that is sometimes present and sometimes below the horizon, following the 17-hour rotation. This transition zone is where the atmospheric dynamics are currently most active as the planet approaches its 2028 northern summer solstice. The circulation patterns are adjusting. The chemistry is responding to the changing geometry of sunlight. And the observations from Hubble, from JWST, from ground-based adaptive optics systems are building a record of this transition that scientists will be studying for decades. A critical data point arrived in the 2007 Uranian equinox, the last time the sun crossed the planet's equatorial plane before the current 2028 solstice. Before 2007, the South Pole had been in summer, and the southern polar cap had been the bright, haze-rich feature observed by Voyager 2 in 1986. After 2007, the northern hemisphere moved into summer, and observations showed the northern polar cap gradually becoming more prominent, while the southern polar cap faded. This transition unfolded over years, not hours. The photochemical haze does not instantly appear or disappear when the sunlight changes. It takes time for the chemical reactions to produce haze, and time for existing haze to settle or disperse. The time constants are not well constrained by current observations, because the equinox transition has only been observed once with modern instruments, and the observations were fragmentary, limited by telescope time allocation and by the capabilities of instruments available in 2007. The 2028 solstice approach, underway right now, represents an opportunity for scientists. As the planet approaches its northern summer solstice, the atmospheric dynamics will change. The polar cap may brighten further. New storm features may develop. The atmospheric banding may become more pronounced. JWST, Hubble, and new ground-based telescopes with adaptive optics will be watching. But there is something that no telescope on Earth can observe about the Uranian seasons, because it happens in the interior. As the pattern of solar heating changes with the seasons, as the pole receives 42 years of warmth and then 42 years of cold, the effect penetrates into the atmosphere to some depth, not deeply. The solar energy reaching Uranus is too weak to heat more than the upper layers of the atmosphere significantly, but to some extent, the change in the upper atmosphere's temperature and composition with season may drive changes in the circulation below, which may in turn affect the rate of mixing between the upper and lower atmosphere. This atmospheric interior coupling is one of the key unknowns in Uranus science. The stable layer deep in the atmosphere, the hypothesized insulating layer that traps the planet's internal heat, may interact with the seasonal circulation in ways that are not yet understood. Does the seasonal circulation penetrate to the stable layer? Does it disrupt it? Does the stable layer influence the atmospheric response to the seasonal forcing? These questions cannot be answered from Earth orbit or even from a flyby. They require an atmospheric probe, an instrument dropped into the Uranian atmosphere that can measure temperature, pressure, and composition at multiple depths as it descends. The proposed Uranus Orbiter and Probe mission, the highest priority large mission in NASA's current Planetary Science Decadal Survey, would carry such a probe. It would be released from the orbiting spacecraft and descend into the Uranian atmosphere, transmitting data for as long as it can function under the increasing pressure and temperature of the descent before eventually being crushed at depth. The data from even a few hours of descent, reaching perhaps a few hundred bars of pressure before the probe fails, would answer questions about the deep atmosphere that have been unanswerable since Herschel first pointed his telescope at a slow-moving object in the constellation Gemini in 1781. You drift in the atmosphere, watching the pale sun trace its slow circle in the polar sky above the northern hemisphere. Below you, the diamond rain continues. Somewhere in the transition between this observable atmosphere and the opaque interior below, the methane continues to dissociate, the carbon continues to crystallize, and the diamonds continue their slow fall toward a core that has never been seen. The season continues its long, slow turn. 42 years of sunlight, then 42 years of night, then 42 years of sunlight, again. The planet does not notice. It rolls on regardless, through its long orbit around a distant sun, maintaining its absurd axial tilt, maintaining its extreme seasons, maintaining its cold and its silence, and its endless production of diamond in the dark. The clouds in the upper troposphere drift past you on the retrograde equatorial wind. The polar cap glows faintly above, brightened by 4 decades of continuous photochemical reaction. The moons, 27 of them, in tilted orbits that reflect the planet's own tilt, move in their paths above the ring plane. The rings themselves orbit in the equatorial plane, tilted 97 degrees from the ecliptic, catching almost no sunlight, barely visible against the black of space. And the planet continues to roll. Not toward anything, not away from anything, simply rolling, as it has been rolling for 4.5 billion years, in the cold and quiet and enormously patient dark of the outer solar system. You breathe with it. In. The long day at the pole. Out. The long night at the other end of the world. The surface of Uranus, if you can call the cloud layer a surface, is not the same at every latitude. The differences are subtle in visible light, but they are real, and they are driven by the extraordinary seasonal cycle. At latitudes between about 45 and 65 degrees in the southern hemisphere, the hemisphere currently moving away from its summer, settling into its long autumn and approaching winter, a distinct atmospheric feature called the South Polar Collar has been observed in Hubble images. The collar is a band of relatively bright cloud at mid-latitudes, marking the boundary between the polar region and the lower latitude atmosphere. It is thought to be a product of the atmospheric circulation that develops around the pole during the long summer, a circulation that concentrates haze at certain latitudes and produces the collar-like feature as a boundary condition of the polar vortex. As the southern summer ends and the southern atmosphere loses its solar driving force, the southern polar collar is expected to fade. In the northern hemisphere, a corresponding collar has been developing as the northern summer builds toward its 2028 peak. The evolution of these features, the fading of the south and the brightening of the north, represents a direct observable consequence of the axial tilt that knocked Uranus onto its side billions of years ago. Every cloud in this atmosphere, every polar cap, every storm feature, every banding structure, all of it traces back to that one ancient collision. You think about what it would mean to experience a Uranian season from the surface, if there were a surface to stand on. At the North Pole, right now, the sun has been above the horizon continuously for approaching 2 decades. It will remain above the horizon for another few years before the geometry of the orbit begins to bring the pole back out of the sun's direct line. During this entire period, roughly 40 years of continuous sunlight, from the 2007 equinox to the 2049 equinox, a hypothetical observer at the North Pole would never see a sunset. The sun would simply circle the sky, slowly rising an angle toward the solstice, and then slowly descending after it, but never dipping below the horizon. The sky would be a uniform brightness, lit by a sun too weak to warm, but bright enough to illuminate. The stars would be invisible during this polar day, washed out by the scattered light. The stars would not return for 2 more decades. At the South Pole, simultaneously, right now, the conditions are the opposite. The sun has been below the horizon for approaching 2 decades. It will remain below the horizon for another 2 more decades. A hypothetical observer at the South Pole would be in continuous night, stars visible at all times, the faint disk of the sun never appearing above the horizon, the sky dark in every direction. The temperature at this pole, deprived of even the weak solar heating that the North is receiving, would be at its coldest. The photochemical haze would be at its minimum. The polar cap, such as it was during southern summer, would be at its faintest. The contrast between the 2 poles is maximum near the solstice, and the 2028 solstice is approaching. No spacecraft will be at Uranus to observe it. The Voyager 2 flyby occurred at the 1986 southern solstice. The southern pole was aimed almost directly at the spacecraft during the approach. The images Voyager 2 captured of the planet showed a nearly featureless disk, the south pole facing the camera, the rings appearing almost as concentric circles around the visible face of the planet. There were almost no visible cloud features. The atmosphere was as quiet as it ever appeared. Astronomers wondered at the time whether the near-featureless appearance was a consequence of the southern summer, the pole-on geometry providing an unusual viewing angle, or whether Uranus was genuinely less active than other giant planets. The subsequent decades of Hubble observations, showing that the atmosphere does develop visible features at other seasons and viewing angles, suggested that some of the Voyager 2 featurelessness was a consequence of geometry, but some of it was real. Uranus is genuinely less active than Jupiter or Saturn, a consequence of its anomalously low internal heat flux. The 2028 solstice will be observed with far superior instruments than existed in 1986 JWST, operational through at least the early 2030s, based on its fuel reserves, will observe Uranus at the northern summer solstice in wavelengths spanning from near-infrared to mid-infrared. The data that will come from these observations, the atmospheric temperatures at multiple levels, the cloud structure at multiple altitudes, the composition of the upper atmosphere near the solstice, will represent the most detailed picture of a Uranian solstice ever obtained. But it will still be a picture taken from 1 billion kilometers away. The proposed Uranus orbiter, if it launches in the early 2030s on the trajectory currently under study, would arrive at Uranus in the mid-2040s after the 2028 solstice, but during the subsequent transition back toward the equinox, it would not observe the northern summer solstice, but it would observe the planet's atmosphere responding to the post-solstice change, the northern polar cap fading, the southern cap beginning to rebuild, the transition zone of the equinox moving southward. For the first time, a spacecraft in orbit would watch the Uranian seasons change. You remain in the atmosphere of the approaching solstice northern hemisphere. The sun circles above you, patient, small, cold. The polar cap extends above the northern horizon, brighter than the surrounding atmosphere, a consequence of 42 years of continuous photochemical reaction. The winds at this latitude are prograde, blowing in the direction of the planet's rotation at hundreds of kilometers per hour. Below you, in the deep interior, the diamonds are falling. They have been falling for billions of years, and they will continue falling for billions of years more. The seasons will cycle again and again, 42 years of sunlight, 42 years of night, 42 years of sunlight, and through every season, at every depth below the visible atmosphere, the carbon will continue to crystallize, and the crystals will continue their slow descent. This is what time looks like at the scale of a planet. Not the time of human history, a few thousand years of written record, a few 100,000 years of anatomically modern humans, a few million years of the genus Homo. The time of a planet is measured in billions of years, in the accumulation of diamond over timescales, so long that the Earth's continents have moved, species have evolved and gone extinct, mountain ranges have risen and eroded, oceans have formed and dried, and stars within 100 light years of the sun have completed their own life cycles. Uranus has been here for 4.5 billion of those years, rolling, making diamonds, rotating on its side through the cold outer solar system, too far from the sun to be warm, too large and strange to be understood from a single flyby, too remote to have been visited more than once. The planet does not know that it is being studied. It does not know that its image has been captured in X-ray, infrared, ultraviolet, and visible light by telescopes on and around a small rocky planet 3 billion kilometers closer to the sun. It does not know that its internal structure is debated in papers and conference talks by scientists who have never been near it and can only infer its interior from the weak signals, gravitational harmonics, magnetic field measurements, atmospheric spectra that reach instruments at Earth's distance. It simply rolls. And in the dark interior, the diamonds fall. The moons of Uranus are named after characters from literature. Not mythology, not the Greek and Roman gods that fill the names of planets and most other moons in the solar system, but characters from the plays of William Shakespeare and the poetry of Alexander Pope. Miranda, Ariel, Umbriel, Titania, Oberon, names from A Midsummer Night's Dream and The Tempest and The Rape of the Lock, Caliban, Sycorax, Prospero, Setebos, more Shakespeare, Belinda, Cressida, Desdemona, Juliet, Portia, Rosalind, more still, The naming convention was established by Herschel himself, who named the first 2 moons he discovered after characters from The Tempest and A Midsummer Night's Dream, and was continued by every subsequent discoverer. There are 27 known moons in total. They range from the large and complex, Titania the largest, with a radius of 788 kilometers, to the small and irregular, captured objects or fragments of larger bodies that orbit at great distances from the planet in inclined eccentric paths. All of them orbit in the plane defined by the planet's equator, the same tilted plane that holds the rings, tilted 97 degrees from the ecliptic. You rise above the atmosphere of Uranus and look outward. The ring system spreads before you in its tilted plane, 13 narrow dark bands of material orbiting at various distances from the planet's center, the innermost rings close and tight against the upper atmosphere, the outermost extending several thousand kilometers further out. Beyond the outer edge of the ring system, the inner moons begin, small dark bodies orbiting in the same plane as the rings, some of them serving as shepherds to the ring material, their gravitational influence maintaining the sharp edges of individual rings. The inner moons, Cordelia, Ophelia, Bianca, Cressida, Desdemona, Juliet, Portia, Rosalind, Cupid, Belinda, and Perdita, are small. Most have radii of only a few tens of kilometers. They are too small to resolve in detail from Earth-based telescopes, and most were discovered either by Voyager 2 during its 1986 flyby or by the Hubble Space Telescope in subsequent years. Perdita was discovered in Voyager 2 data in 1999, 13 years after the flyby, when scientists re-examining the archived images found a faint object that had been missed in the original analysis. Cupid and Mab were discovered by Hubble in 2003. The inner moons are not stable on astronomical timescales. Their orbits are packed close together, and numerical simulations of their gravitational interactions suggest that collisions between them are likely to occur within the next few 100 million years. The solar system is not a static place. Even the moons of a quiet planet in the outer solar system are engaged in a slow gravitational dance that will eventually result in collisions, fragmentation, and the renewal of ring material from the debris. You move outward through the ring system. The epsilon ring is the most prominent structure you pass through, the widest, the brightest, the most carefully studied of the Uranian rings. It was the first of the rings discovered in the 1977 occultation observation. Its width varies from about 20 kilometers at its narrowest points to about 100 kilometers at its widest. Because the ring is not circular, it is slightly elliptical, and the width varies as the material moves through its orbit. At the narrowest points, the ring is more compressed. At the widest, the material spreads slightly. Cordelia and Ophelia flank the epsilon ring, Cordelia orbiting just inside its inner edge, Ophelia just outside its outer edge. Their gravitational resonances with the ring material act as walls, preventing the ring from spreading radially. A ring without shepherd moons would gradually disperse. The collisions between ring particles scatter them into slightly different orbits, and over time the ring broadens and flattens. The shepherds counteract this by gravitationally nudging particles that stray toward the ring edges back into the ring. The mechanism is elegant in its simplicity. 2 small moons, each less than 30 kilometers in radius, maintaining a ring structure through gravity alone, a continuous dynamic balance between the spreading tendency of particle collisions and the confining force of orbital resonance. You clear the outer edge of the ring system and enter the space where the larger moons orbit. Miranda is the innermost of the 5 large moons, orbiting at a distance of about 129,000 kilometers from the center of Uranus, roughly 1/3 of the distance from Earth to the Moon. It is the smallest of the 5 major moons, with a radius of 235.8 kilometers, but it is not the least interesting. Miranda is in many ways the most geologically remarkable object in the Uranian system, possibly in the entire outer solar system. You descend toward Miranda. The surface comes into focus as you approach, a chaotic patchwork of terrains, wildly different from each other, juxtaposed in a way that seems almost random. Ancient, heavily cratered terrain sits immediately adjacent to younger, grooved terrain with no craters at all. Smooth plains are cut by networks of canyons. And rising from the surface, in one of the most striking landforms anywhere in the solar system, are the coronae. Miranda's coronae are roughly rectangular to oval regions of concentric ridges and grooves, each hundreds of kilometers across, with sharp, clear boundaries against the surrounding terrain. 3 major coronae have been identified and named: Arden, Elsinore, and Inverness, all names from Shakespeare's plays. Their formation is not fully understood. Early theories proposed that Miranda had been shattered by a large impact and reassembled in a chaotic configuration, the different terrain types representing fragments of a disrupted interior that had been jumbled and reaccreted. More recent analysis has favored an explanation based on upwelling of warm material from the interior, a process called diapirism, in which a denser material overlying a less dense material becomes gravitationally unstable, and the less dense material rises in plumes, deforming the surface above it. The coronae may represent the surface expression of these rising plumes, regions where warm, low-density material from the interior pushed upward and deformed the overlying crust into the distinctive concentric ridge and groove patterns observed today. But the most spectacular feature of Miranda is not the coronae. It is the cliff. Verona Rupes is an escarpment, a fault scarp, on the southern hemisphere of Miranda. It was imaged by Voyager 2 during the 1986 flyby, appearing in images as a dramatic, nearly vertical face cutting across the surface. Subsequent analysis of the Voyager images measured its height at approximately 20 kilometers, 20,000 meters, making it the tallest known cliff face in the solar system. For comparison, the tallest cliff on Earth is generally cited as Baffin Island's Mount Thor, with a vertical drop of about 1,240 meters, roughly 1.2 kilometers. Verona Rupes is approximately 16 times taller. You stand at its edge. The surface of Miranda is ice, water ice mixed with rock, compacted and ancient, scarred by impact craters, and cut by the tectonic processes that formed the coronae. The gravity here is extremely low. Miranda's surface gravity is approximately 0.079 meters per second squared, about 0.8% of Earth's surface gravity. A person of average mass on Earth would weigh less than half a kilogram on Miranda's surface. At the edge of Verona Rupes, you look down. The cliff face drops 20 kilometers. At the bottom, the icy plain of Miranda's southern terrain extends away, flat and cratered. The drop is so great and the gravity so low that if you stepped off the edge, if you simply leaned forward and fell, you would not land quickly. At Miranda's surface gravity, a falling object accelerates at only 0.079 meters per second. Starting from rest at the top of the cliff, it would take approximately 71 seconds to fall the first 100 meters. The total fall time from the top of Verona Rupus to the base would be approximately 10 minutes. 10 minutes of falling in near silence, watching the cliff face slide past. You step back from the edge. Above you, above Miranda's thin, non-existent atmosphere, in the black sky of the outer solar system, Uranus hangs enormous, its pale blue-green disk filling a large fraction of the sky. The planet's rings are visible as a thin line across its equatorial plane, tilted steeply relative to Miranda's orbital path. The sun is a bright point far away, providing the weak light that illuminates this scene, enough to see by, but not enough to warm. From Miranda's surface, Uranus appears roughly 16 times larger in angular diameter than the full moon appears from Earth. It is not a beautiful sight in the way a sunset is beautiful. There is no color gradient, no atmosphere to scatter and redden the light, but it is vast. An enormous pale sphere against the black, its rings a thin bright line, its face smooth and quiet. You look at it for a long time. Then you rise from Miranda's surface and continue outward to the larger moons. Ariel, orbiting at about 190,000 kilometers from the planet's center, is the most geologically active-looking of the 5 major moons. Its surface shows extensive networks of canyons and valleys, grabens formed by extensional tectonics, where the crust has been pulled apart and blocks of crust have dropped between parallel fault lines. The canyon floors are smooth, suggesting they have been resurfaced by viscous icy material that flowed into them after they formed, a process called cryovolcanism, the eruption of icy or briny fluid from the interior rather than molten rock. Some regions of Ariel's surface are almost completely free of impact craters, indicating they are geologically young, resurfaced relatively recently in geological terms, possibly within the last billion years. Umbriel, orbiting just outside Ariel at about 266,000 kilometers, is almost the opposite of Ariel in surface appearance. It is the darkest of the 5 major moons, with a surface albedo of only about 18%. Dark, uniformly cratered, ancient-looking, its surface shows very little evidence of geological activity. The most notable feature is a bright ring near the North Pole, designated Wunda, with an albedo much higher than the surrounding terrain. The composition of Wunda is unknown. It may be a deposit of bright material, possibly carbon dioxide ice, or some other volatile, but no definitive identification has been made from the available data. The contrast between Ariel and Umbriel, 2 moons of similar size orbiting near each other, one geologically young and resurfaced, the other ancient and unchanged, is one of the unexplained puzzles of the Uranian moon system. Why does Ariel show so much geological activity and Umbriel so little? The answer likely involves the thermal history of the moons and their past orbital resonances, periods in the past when their orbits were in a mathematical ratio that caused periodic gravitational forcing, generating tidal heating in the interior. But the specifics remain incompletely understood. Titania, the largest moon, orbits at about 436,000 kilometers. Its surface is intermediate between Ariel and Umbriel, moderately cratered, with evidence of past geological activity in the form of fault scarps and canyon systems, but not as dramatically resurfaced as Ariel. Titania may harbor a subsurface ocean, a layer of liquid water between the icy crust and the rocky interior, though this is a hypothesis based on thermal models rather than direct observation. The conditions for maintaining liquid water in Titania's interior are marginal and depend on the amount of radioactive heat-generating elements present in the rock component of the moon. Oberon, the outermost of the 5 major moons at about 583,000 kilometers from the planet's center, is the second largest, with a radius of 761.4 kilometers, close to Titania's 788. Its surface is heavily cratered, the most heavily cratered of the large Uranian moons, suggesting it has not been significantly resurfaced since early in solar system history. Several large impact basins are visible in the Voyager 2 images, some with dark floors, suggesting that fluid material, possibly a water-ammonia mixture from the interior, seeped into them after the impacts and then froze. On the rim of one of Oberon's large craters, a mountain rises to an estimated height of 6 kilometers above the surrounding terrain. Like so much else about the Uranian moons, this feature, dramatic, isolated, unexpected, has not been named or fully characterized. The Voyager 2 images showed it, but could not resolve it in detail, and no subsequent spacecraft has returned to image it further. You move from moon to moon, across the tilted system. Each moon presents its own version of what an icy world in the outer solar system can be. Ancient and dark like Umbriel, geologically young and canyon-filled like Ariel, chaotically terrained and cliff-edged like Miranda, moderately active and possibly ocean-bearing like Titania, heavily cratered and mountain-rimmed like Oberon. None of them has been visited by a spacecraft since 1986. None of them has been imaged at high resolution since the Voyager 2 flyby. The best images of most of these moons, the most detailed views of their surfaces, their craters, their canyons, their cliffs come from a spacecraft that flew past in 6 hours nearly 4 decades ago, during a brief window of closest approach, with cameras and instruments designed in the 1970s. Everything known about these worlds fits in 6 hours of data from 1986. The science community has pushed for a return for decades. The Uranus Orbiter and Probe mission, prioritized in the 2022 Decadal Survey, would not only orbit the planet, but would conduct multiple close flybys of the major moons during its time in the Uranian system. Each flyby would provide imaging, spectroscopy, and geophysical data orders of magnitude beyond what Voyager 2 could obtain. The question of whether Ariel or Titania harbors a subsurface ocean, a potentially habitable environment, in the broadest sense of that word, could be answered. The question of what formed Miranda's coronae could be resolved. The composition of Umbriel's bright Wanda feature could be determined. The mountain on Oberon's crater rim could be named and measured. All of this is possible. None of it has happened yet. You drift outward from Oberon, leaving the regular moon system behind. Beyond Oberon, at much greater distances and in orbits that are inclined and eccentric rather than circular and equatorial, lie the irregular moons, 9 of them currently known. They are small, radii of 10 to 90 kilometers, and dark. They are believed to be captured objects, small bodies from the outer solar system, perhaps from the scattered disk or the Kuiper belt, that passed through the Uranian system in the past and were captured by the planet's gravity into distant, irregular orbits. Their names continue the literary tradition, Caliban, Sycorax, Prospero, Setebos, Stefano, Trinculo, Francisco, Margaret, Ferdinand, all from Shakespeare, mostly from The Tempest. Caliban and Sycorax are the largest of the irregular moons, with radii of about 36 and 75 kilometers respectively. These distant, irregular moons orbit far from the planet. Sycorax, for instance, orbits at a distance of about 12 million kilometers from Uranus, more than 20 times the distance of Oberon. At these distances, the planet's influence is weak and the objects are loosely bound. Their orbits are inclined to the equatorial plane, some of them in retrograde orbits, moving in the direction opposite to the planet's rotation, which is a strong indicator of capture rather than formation in place. The outer solar system is littered with the survivors of the early chaotic period, small bodies flung into distant, irregular orbits by the gravitational scattering of the giant planets as the solar system settled into its current configuration. The irregular moons of Uranus are a local example of this population, a handful of bodies that happen to pass close enough to be captured, now permanently bound to a world that is itself the product of ancient violent events. You rest here, far from the planet, in the cold outer reaches of the Uranian system. From this distance, Uranus itself is still visible, a pale blue-green disk, noticeably smaller than it appeared from Miranda's surface, but still clearly a sphere rather than a point. The rings are invisible at this distance, too thin, too dark, too small against the planet's disk. The 5 large moons are visible as faint points of light near the planet, too small to resolve as disks. The sun is a very bright star, unmistakably the brightest object in the sky, but not a disk to the naked eye at this distance. It provides a cold, clear light that illuminates the surfaces of the moons and the rings and the planet's atmosphere with the same physics that illuminates Earth's surface. Photons traveling at the speed of light, carrying energy across 2.9 billion kilometers, arriving here still coherent, still warming, still driving photochemistry in the upper atmosphere of the planet below. The light that left the sun 8 minutes ago reached Earth. The light that left the sun 2 hours and 40 minutes ago is arriving at Uranus right now. By the time it arrives, it carries only a fraction of the intensity it had at Earth, following the inverse square law, intensity decreasing with the square of the distance. At Uranus's distance, sunlight is approximately 360 times less intense than at Earth. And yet it is enough to give the planet its color, enough to drive the photochemistry of the polar cap, enough to illuminate the surfaces of 27 moons, enough to be detected by telescopes on Earth and used to infer the composition of the atmosphere, the structure of the rings, the albedo of the moon surfaces. Light carries information across any distance. In, out. The cold of the outer solar system is not cold in the way a winter morning is cold, a temperature felt on skin, a sensation registered by nerve endings. It is cold in the way space is cold, an absence of thermal contact, a vacuum that holds no molecules to conduct heat away from a body, a temperature defined not by the air around you, but by the radiation balance between what is received and what is emitted. In the vacuum between the moons, the temperature of an object in thermal equilibrium with the incoming sunlight at this distance is approximately 59 Kelvin, negative 214 degrees Celsius. An object that absorbs sunlight efficiently and radiates efficiently will sit at roughly this temperature. The moons, with their low albedos and rocky icy compositions, are at temperatures close to this. The planet's upper atmosphere, as measured by Voyager 2, is colder still, down to 49 Kelvin at the tropopause, the temperature minimum that makes Uranus the coldest planetary atmosphere in the solar system. You remain here between the moons in the cold and the silence. The Uranian system is quiet. There are no active volcanoes erupting into the vacuum, unlike at Io, where Jupiter's tidal forces drive continuous volcanic eruptions. There are no geysers of nitrogen erupting from the surface, unlike at Triton, Neptune's captured moon. There is no detected geological activity happening right now, in real time, anywhere in the Uranian system that can be monitored from Earth. The system is ancient and mostly still. But it was not always still. The coronae of Miranda, the canyons of Ariel, the resurfaced terrains of Titania, all of these speak to a past in which the Uranian moons were geologically active, driven by tidal heating from orbital resonances that may no longer exist. The orbits that caused the resonances have shifted. The tidal heating has ended. The geological activity has ceased, leaving its record in the surfaces of these worlds as a kind of frozen history. The solar system is full of frozen histories. The craters on the moon record the bombardment history of the inner solar system. The layered sediments of Mars record ancient wet periods. The coronae of Miranda record a period of tidal heating that ended billions of years ago. Each world carries its past in its surface, in its composition, in its orbital parameters, a record that can be read imperfectly by instruments designed by beings on a small rocky planet 3 billion kilometers closer to the Sun. Uranus itself is the largest frozen history in its own system, a planet knocked onto its side by an ancient collision, carrying that tilt forward through every orbit it has completed since, unable to right itself, maintaining the record of that one violent moment. You look back at the planet from the distance of the outer moons. The pale blue-green disk, the thin line of the rings, the orbiting points of the major moons, the distant faint sun. This is the Uranian system as it exists right now, as it has existed, largely unchanged in its large-scale structure, for billions of years. The rings shift slowly, fed by small moons and depleted by the outward drift of particles. The moon's orbits evolve slowly under mutual gravitational perturbations. The planet's magnetic field wobbles in its asymmetric pattern. None of it is fast enough to watch on a human timescale. The system simply is. You begin to move inward again, back toward the planet, through the ring plane, into the atmosphere, settling into the quiet of the deep troposphere as the polar cap glows above and the winds move in their invisible, enormous flow around you. The planet rotates beneath you, one full rotation every 17 hours. The last time a spacecraft was this close to Uranus, it was January of 1986, and the world was different. The Cold War had not ended. The internet did not exist. No exoplanet had been confirmed. The concept of superionic water was theoretical. The 2017 laboratory confirmation of diamond rain was 3 decades away. The James Webb Space Telescope was an idea in someone's proposal document. Voyager 2 gathered its data in 6 hours and kept moving. In the decades since, Uranus has continued its orbit. One full revolution completed in 1986, another in 2070. It is currently past the midpoint of its second orbit since the flyby. The planet has rotated on its axis approximately 49,000 times since Voyager 2 passed. The diamonds have continued to fall. The seasons have continued their long, slow turn. And no spacecraft has returned. The magnetic field of Uranus wobbles through its asymmetric rotation, sweeping outward through the magnetosphere in patterns that were measured for only 6 hours and have been modeled extensively but never reobserved in situ. The interior structure of the planet, the depth and composition of the ice mantle, the size and temperature of the rocky core, the specific structure of the superionic water layer, remains constrained only by the models and by Voyager 2's measurement of the gravitational harmonics, which encode information about the internal mass distribution. The atmosphere has changed since 1986. The southern polar cap, bright and prominent when Voyager 2 observed it at the southern summer solstice, has faded as the southern hemisphere moved into autumn. The northern polar cap, invisible in 1986, has grown as the northern summer has progressed. The atmospheric dynamics observed by Hubble in the 2010s and 2020s are different from what Voyager 2 saw. More clouds, more structure, more variation. The planet is not static, it is changing on the timescales that planets change, slowly, continuously, seasonally. And watching it from Earth, with instruments that gather photons that traveled for 2 hours and 40 minutes before arriving in the telescope's focal plane, scientists are trying to understand a world they have visited exactly once. 40 years of watching from a distance, one brief visit, so much still unknown. You settle deep into the atmosphere of Uranus. The winds move around you, the polar cap glows above, dimly. The rings trace their narrow paths in the same tilted equatorial plane. The moons turn in their long paths. The planet rotates, the seasons turn. The magnetic field sweeps outward in its wobbling asymmetric pattern, generated in the superionic water deep below, offset from the center, tilted from the rotation axis, unlike any other magnetic field in the solar system. The last signal from Voyager 2, after its Uranian flyby, continued outward, past Neptune, past the heliopause, into interstellar space. Voyager 2 is still operating as of the mid-2020s, its power supply slowly declining, its instruments still returning data from the space between the stars. It carries, on a gold-plated copper disc, sounds and images from Earth, a record intended for any intelligence that might someday find it. It left Uranus behind in January of 1986, and it has not looked back. The planet watched it go in the way that planets watch things, which is not watching at all, simply existing in the path of departing light, and has been rolling on since then, turning on its axis, unchanged. Patient, enormous, strange. The sentences can be shorter now. The pace can slow. The atmosphere around you grows quiet. The wind, for all its 900 kilometers per hour, makes no sound in a medium with no ears to hear it. The polar light, not an aurora, not warm, just the faint illumination of a sun too far away to be felt, holds steady above the northern horizon. The planet turns beneath you, slowly, and the moons trace their paths above, 27 of them, named for characters who fell in love, who made mischief, who were shipwrecked, who were banished, who were enchanted, who were found. Miranda, Ariel, Umbriel, Titania, Oberon. Their names come from stories of transformation and loss and wonder. Their surfaces carry records of geological time. Their orbits are tilted 97 degrees from the rest of the solar system, following a planet that was knocked sideways billions of years ago and never recovered. The system is at rest in its own way. Out, carbon is still crystallizing in the dark below, as it has for billions of years. The seasons are still turning above. You are here in the atmosphere of a world that has been here since before the Earth had oceans. That has been making diamonds in its interior since before the first single-celled life appeared on Earth. That has 27 moons, each with its own history, its own geology, its own frozen record of a solar system in the process of becoming what it is now. That has been visited once. That is waiting patiently in the cold, in the dark, in the silence, to be visited again. If you are still awake, if the weight of 4.5 billion years and the slow fall of diamond through hot dark fluid and the long seasons of a tilted world have not yet carried you somewhere quieter, then you have traveled further tonight than most people travel in a lifetime of reading. You have been inside an ice giant. You have watched diamonds form and fall. You have stood at the edge of the highest cliff in the solar system. You have floated between moons named for Shakespeare in the tilted orbital plane of a planet that refuses to spin the way planets are supposed to spin. The story of Uranus is in many ways the story of what planetary science does not yet know. Among the 4 giant planets, Jupiter and Saturn have each received dedicated orbiters. The Galileo spacecraft orbited Jupiter from 1995 to 2003, and the Cassini spacecraft orbited Saturn from 2004 to 2017. Both missions transformed what was known about their target planets, revealing details and dynamics that no flyby or Earth-based observation could have uncovered. The moons of Jupiter were found to include Io, with its active volcanism, and Europa, with its subsurface ocean now considered one of the most likely places in the solar system to find extraterrestrial life. Saturn's moon Enceladus was found to be actively venting water vapor and organic compounds into space from a subsurface liquid water ocean. Uranus and Neptune have received no such attention. The only measurements taken from within their systems came from Voyager 2, which visited both on the same outbound trajectory and never returned. This is not for lack of scientific interest. It is a consequence of funding priorities, mission complexity, and the enormous distances involved. A mission to Uranus takes years to reach its target. The proposed Uranus orbiter would require approximately 12 to 13 years of transit time, depending on the launch trajectory and the availability of planetary gravity assists. A mission launched in the early 2030s would arrive in the mid-2040s. Planning a mission that will not arrive at its destination for more than a decade requires a sustained commitment of funding and scientific community support that is difficult to maintain across budget cycles and political administrations. But the scientific case is strong. Uranus is not merely an interesting planet. It is a representative of an entire class of worlds, the ice giants, that appear to be among the most common types of planet in the galaxy. Understanding how Uranus formed, how its interior is structured, how its magnetic field is generated, how its atmosphere evolves through its extreme seasons, and how its moons developed their varied geological histories, would provide a template for understanding hundreds of similar worlds orbiting other stars. The exoplanet population discovered by the Kepler Space Telescope and subsequent surveys has revealed that planets in the size range of 2 to 4 Earth radii, the range that includes Uranus at approximately 4 Earth radii, are extraordinarily common. They appear more frequently in the known exoplanet sample than any other size category. Many of these worlds orbit close to their host stars, in orbits far shorter than a year, and are therefore exposed to levels of stellar radiation far exceeding what Uranus receives. Their atmospheric evolution, their internal structure, their potential for habitability in any form, all of these questions are connected to what is known and unknown about Uranus and Neptune. A well-studied Uranus is a better lens for understanding these distant worlds. You drift in the upper atmosphere, thinking about distance. 2.9 billion kilometers. That is how far you are from Earth right now, in the terms of Uranus's average orbital distance. Light traveling at 299,792 kilometers per second takes approximately 2 hours and 40 minutes to cover that distance. A radio signal, which also travels at the speed of light, takes the same amount of time. When Voyager 2 transmitted its data from the Uranian system in January of 1986, the signals took 2 hours and 45 minutes to reach Earth, where they were received by the large dish antennas of the Deep Space Network. The Deep Space Network, a system of large radio telescopes operated by NASA and located in California, Spain, and Australia to provide continuous coverage as the Earth rotates, was the thread connecting Voyager 2 to the scientific teams waiting for its data. The antennas are 70 meters in diameter, designed to receive the incredibly faint signals transmitted by spacecraft at planetary distances. The signal strength from Voyager 2 at Uranus was 20 billion times weaker than the power of a digital watch battery. That was the signal that carried the first close-up images of Uranus and its moons back to Earth, 20 billion times fainter than a watch, traveling for 2 hours and 45 minutes at the speed of light, collected by a 70-meter dish in the California desert, and amplified into data that could be processed and displayed. The engineering required to accomplish this is as extraordinary as the science it enabled. The atmosphere shifts around you. The slow circulation of the polar vortex moves you gently. The temperature is constant, 50 Kelvin in the upper troposphere, as it has been for all the time you have been here. The faint sun traces its low arc toward the northern horizon. Uranus was always going to be a difficult planet to understand. It is far away. Its atmosphere is nearly featureless in visible light. Its interior is opaque to all forms of radiation that could be used to image it remotely. Its moons are small and were, until Voyager 2, almost entirely uncharacterized. Its rings are dark and narrow. Its magnetic field was entirely unknown before the 1986 flyby. And yet there is now a substantial body of knowledge, built from 2.5 centuries of observation, from one 6-hour flyby, from decades of Hubble monitoring, from the first years of JWST science, from sophisticated theoretical modeling and laboratory experiments that replicate the planet's extreme interior conditions in miniature on Earth. The knowledge is fragmentary, the gaps are enormous, but it is real and it is growing. Every observation of Uranus from Earth, every photon collected by a telescope, every spectrum analyzed, every cloud feature tracked across successive images, adds to the understanding of a world that billions of years of existence have not made simple. The process continues, indifferent to observation. The seasons are turning right now. The magnetic field is wobbling right now in its asymmetric offset pattern, generating a magnetosphere unlike any other in the solar system. And you are here in the atmosphere at the top of the troposphere, where the temperature is 49 Kelvin and the methane absorbs red light and gives the planet its color, present in the way that imagination and scientific knowledge together make presence possible. The concept of presence in science is not mystical. It is the result of data, measurements taken by instruments, models validated by observations, laboratory experiments that reproduce extreme conditions in miniature and confirm that the predictions of physics hold even at pressures and temperatures never experienced by any human. When scientists say that the interior of Uranus likely contains superionic water, they are not speculating. They are extrapolating from thermodynamic principles confirmed by laboratory experiment to conditions that are more extreme but obey the same physical laws. The diamonds inside Uranus are real in exactly this sense. They have not been directly observed. They cannot be directly observed with any technology currently available. But the physical process that produces them, carbon crystallization under extreme pressure, has been confirmed experimentally, and the conditions required for that process are known to exist in the interior of Uranus. The diamonds are as real as any object whose existence is confirmed by the reliable application of confirmed physical principles to confirmed conditions. This is how science reaches across distances too large for any machine to have traveled. You have been inside Uranus tonight, in the ice mantle, in the region of diamond formation, in the upper troposphere, at the edge of Miranda's Cliff, between the moons in the cold of the outer system, because science has been there first, one measurement at a time, one publication at a time, one laboratory experiment at a time, building a picture of a world that remains mostly unvisited and mostly unknown. The picture is incomplete. It will become more complete when the next spacecraft arrives, when the Uranus orbiter, if it launches in the early 2030s, finally enters orbit around this tilted, cold, diamond-raining world and begins the work of decades-long systematic observation that Galileo did for Jupiter and Cassini did for Saturn. Until then, the planet rolls on. The pace of narration slows here. The sentences are shorter now. There is no urgency in the outer solar system. Everything moves on timescales too long for urgency to mean anything. It has been rolling since the solar system was young. It will roll for billions of years more. The diamonds fall. The moons turn in their tilted orbits. The rings orbit in their narrow, dark bands, shepherded by small moons whose gravity maintains their edges. The polar cap holds its 42 years of photochemical haze in the continuous sunlight of the approaching northern solstice. The magnetic field wobbles outward in its asymmetric sweep, and the temperature at the tropopause holds steady at 49 Kelvin, the coldest planetary atmosphere in the solar system, maintained by a stable layer deep below that refuses to let the internal heat escape. In, the atmosphere carries you. Out, slowly. The planet rotates beneath you, one turn every 17 hours and 14 minutes. moving through the outer dark as it has always moved. Patient, cold and strange, and full of diamond and silence. You have traveled farther tonight than the distance light covers in 2.5 hours. You have been inside a world that has never fully been explored. You have watched a planet make diamonds in its own dark interior, slowly, continuously, without purpose, simply because the physics of carbon under pressure requires it. You have felt the weight of a 42-year season, a winter longer than most human lifetimes, a summer longer than most careers. You have stood at the top of the tallest cliff in the solar system and looked down 20 kilometers to an icy plain that has not changed since the tidal heating that shaped it ended billions of years ago. Let the weight of those distances settle. Let the slow falling of diamonds in the dark become the rhythm of your breathing. Let the long season turn without you having to watch it turn. The planet is there. It will still be there when you wake. Nearly 3 billion kilometers from the sun, rolling on its side, making diamonds, holding its long, cold, patient silence. If this is the kind of story that found you tonight, a subscription to Quiet Science at Bedtime means everything. It helps more people find their way to the outer solar system on nights when sleep comes slowly. Everything you heard tonight is real. Uranus is out there right now. Good night.